Welcome to the Materials Science lecture on bonding-related properties. In this session, we will explore the fundamental aspects of bonding and how they influence various material properties. By the end of this class, you will be able to define key bonding-related properties such as melting point, elastic modulus, and coefficient of thermal expansion. Additionally, you will learn to correlate these properties to a material's atomic bonding potential and atomic bonding force curve. Understanding reversible work is crucial. Hooke's law states that force is proportional to elongation, represented by F equals kx or k equals Fx. This relationship helps us comprehend how materials respond to applied forces. Material stiffness is measured using stress and strain. The slope of the stress-strain curve, known as Young's modulus, indicates the stiffness of a material. This concept is vital for determining how materials deform under load. The coefficient of thermal expansion, denoted as alpha, describes how a material's length changes with temperature. This property is essential for understanding how materials expand or contract with thermal variations. Let's apply our knowledge. Based on the information provided, which type of bonding is associated with the largest and smallest coefficients of thermal expansion? This inquiry will help solidify your understanding of bonding types and their thermal properties. Here are the answers. Covalent molecular solid bonding is associated with the largest CTE, while epoxy resins exhibit the smallest CTE. This comparison highlights the diverse thermal behaviors of different bonding types. Bonding at the atomic level involves a balance between attractive and repulsive forces. The net force, F net, is the sum of these forces, and at zero force, the energy is at its lowest, indicating stable bonding. Bonding energy is modeled using the atomic bonding force curve. The net force is derived from attractive and repulsive forces, providing insights into the stability and strength of atomic bonds. The atomic bonding potential well illustrates how potential energy varies with distance between atoms. The equilibrium separation occurs where the net force is zero, indicating a stable bond. Bond strength is related to macroscopic properties such as stiffness, melting temperature, and thermal expansion coefficient. Stronger bonds result in deeper potential wells, indicating higher energy and stability. Melting point, Tm, is directly related to bond strength. Higher bond energy results in a higher melting temperature, demonstrating the correlation between atomic bonding and thermal properties. Another inquiry moment. Determine the equilibrium spacing between atoms where net forces and potential well are balanced. This exercise reinforces your understanding of atomic interactions and bond stability. The equilibrium spacing occurs at the point of balance where attractive and repulsive forces are equal. This concept is crucial for understanding the stability and behavior of atomic bonds. In this chapter, we reviewed bonding-related properties and their correlations to atomic structure and interatomic bonding. These insights are fundamental for understanding material behavior and properties. This presentation contains copyrighted material used under the Fair Use Doctrine for educational purposes. All rights belong to their respective copyright holders. Links to relevant resources are provided in the video description. Thank you for watching. Please like, share, and subscribe to this channel. We encourage you to comment below with your thoughts and questions. What did you learn from the video, and what topics would you like to explore further?